Thank you. Thanks for the opportunity to speak here. I wish I could be there in person. It sounds like there are a lot of nice conversations going on. Um, I'm going to tell you about some of our recent works on the simulation algorithms for non-Hermitian dynamics. Um, Primarily, I'm going to answer the following two questions. The first question is how to simulate a non-Hermitian dynamics where the Hamiltonian comes with gains or losses, right? And so we tried to answer this question with this paper that we wrote last summer. And more recently, we thought about simulating stochastic dynamics. So we want to answer the question about whether we can simulate a system of SDEs and the corresponding statistics. And we presented an extension of the previous algorithm, and you can find more details in the second paper. Now, these are highly relevant in the conversations about open quantum systems. Obviously, non-Hermitian dynamics is a big part of open quantum system. And this is also related to imaginary time evolutions or ground state or thermal state computations. And toward the end, I'll mention a trivial application to the simulation of non-Markovian open quantum system. And the first thing that I want to kind of say a few words about is where non-Hermitian dynamics are coming from. Now, in quantum chemistry, the biggest example is the diffusive quantum Monte Carlo method. I would probably give credit to my colleague in our chemistry department. Now, more recently, there are some other interesting applications of this. For example, the skin effects. And here, the Hamiltonian is naturally non-Hermitian. I'm in the applied math community. I'm surrounded by mathematicians who work with PDEs on a regular basis. So most of the PDEs that we have to work with do not follow unitary dynamics. So those are kind of three key applications that we have in mind. Now, this talk is about building quantum algorithms to simulate these non-Hermitian or non-unitary dynamics. Now, the idea is to map them to a Hermitian dynamics or unitary dynamics, or more generally, quantum channels. And this is what I'm going to tell you today. Now, the first thing is this question about turning a non-Hermitian dynamics to a Hermitian dynamics. And so in other words, we could have a dynamics that doesn't look like the Schrodinger equation at all, but somehow we want to apply a mathematical mapping to turn it into the Schrodinger equation. Now, the simplest idea, I cannot go back. I couldn't find like who started this first. The first idea, this is used in quantum imaginary time evolutions, is to use a poly Y matrix to dilate the dynamics into a bigger Hilbert space and simulate this dilated system, which follows the unitary dynamics. But this dilation is not exact. So I'm going to focus on some of the ideas that, in principle, at some level, gives you an exact mapping. And so one of the pioneering works is the Schrodingerization idea. You can sort of try to kind of follow their formulation by writing your problem in this ODE setting. You can also give it as a PD. You can single out the part that is Hermitian. So I kept this I on the right-hand side. Right? The part that's not Hermitian shows up in this matrix K. Right? And what they do is they introduce another variable P, and they multiply the solution by this exponential function. What's nice about this exponential function is that its derivative is the same as itself. Therefore, you get an extra differential operator for free. And what that then happens is that by applying sort of appropriate boundary conditions, this differential operator is a skew Hermitian operator. And suddenly, the right-hand side, this term here can be written as negative I times the Hermitian matrix or Hermitian operator, right? So in principle, this kind of elevates the system into a bigger dimension with this additional variable P, where you solve the Schrodinger equation. Now, another important development is the linear combination of Hamiltonian simulations. And this is based on the following formula for representing the dynamical map for this dynamics here. And this is written as an integral here, where on the right-hand side, you are seeing this matrix exponentials, but suddenly in front of the matrix K, you get this extra I. Therefore, it's becoming a unitary operator. And so after the quadrature approximations, you naturally get a linear combination of unitaries. And so there are some existing quantum algorithms that you can take off of the shelf and apply that here. Now, what I'm showing you here are simplified versions of those formulas. And so both of these algorithms can handle time-dependent cases, like where A depends on T, and they have been improved to near optimal complexity. And so the motivation for our first paper last year was to kind of add more dilation schemes to this list. And so we were wondering about whether there are more embedding schemes that can also map this general non-unitary dynamics to the Schrodinger equation. And my starting point is the same as before. So I'm going to keep the part that is already Hermitian. I'm going to work on this extra term here and somehow turn it into this negative I times a Hermitian term. And I'm going to follow the this structure here to build the dilated Hamiltonian. So for the first part, this H is already Hermitian, so I'm not going to do this. I'm not going to do anything extra to this. I'm just going to use this trivial dilation with the identity operator on the ancilla. The key component here is this skew Hermitian operator on the ancilla that helps to elevate this K here into a Hermitian part. And the general pipeline is the following. So I'm going to pick a vector or a function in the ancilla space, tensor product with the initial condition of this dynamics. So that takes me to the dilated Hilbert space. In that Hilbert space, I'm going to solve a Schrodinger equation that is generated by this dilated Hamiltonian, which is Hermitian. Okay. When I'm done, I'm going to project or select. So I'm going to let the ancilla collapse on some state. So I'm going to think of this as a linear functional. Right? And then that takes me back to original physical space. Okay. And the three elements that you can pick here are the function R, the operator F, and this functional L. Okay, so there are kind of three elements that you can pick. The recipe that I came up with is a moment matching condition. And so specifically, this formula that you build will recover the solution of the original dynamics if these three elements exactly satisfy these moment conditions. So you apply the operator f k times, k is any positive integer, including 0, to r, the k times, and then left multiply this by L, you always get 1. As long as this is the case, you recover the exact solution. Okay. Now, the obvious choice would be you pick R so that it is an eigenfunction of f with eigenvalue 1, and then the inner product between L and R is 1. But you see the obvious kind of contradiction here. So since f is a skew Hermitian matrix, how can it have an eigenvalue 1, right? So in order for this to happen, R has to be an unnormalized state. It has to be outside of this Hilbert space. Okay. Now, are there any concrete choices? right? So this kind of formula shows you some very concise conditions in order to guarantee an exact dilation or exact mapping. It turns out that the Schrödingerization can be kind of viewed as one of the moment-fulfilling dilations. So the corresponding operator F is exactly this differential operator. And the function R, or the vector R on the right-hand side, is e to the negative p, right? For the choices of the functional L, there are many choices. So you can evaluate or you can integrate. So there are multiple choices. Now, there's also a connection between Schrödingerization and linear combination of Hamiltonian simulations. So you can take this triple here and apply a similarity transformation using Fourier transform, and you get the same formula as linear combination of Hamiltonian simulations. That being said, in those papers, they rely on different algorithms. Okay. Now, the question is, aside from these two, are there other choices? Right? And this is what we found. So we found a bunch of them, and we can also parameterize them. So the first family here is going to be a set of differential operators. Now, this can be placed in a compact domain so that you don't have to worry about cutting off some long tails for the far field. And the eigenfunctions are these p to some power, and you can pick this free parameter theta so that this becomes a polynomial, and then it becomes really nice to work with. Now, there are also integral operators, like this Laplacian kernel, or pseudo-differential operators. I don't know if these will ever be useful. On the other hand, for the last two the exact dilation schemes, for the difference operator, you can imagine that implementing this on digital quantum computers, or the one based on the Bargmann-Fock operator, you can think about using this on analog or quantum optics-based quantum platforms. And we have some numerical examples for that. But I'm going to, for the next few slides, I'm going to focus a little bit more on the first family here. This is also based on the differential operator. And you can implement this without using Fourier transform. And so I'm going to set it up as follows. So the differential operator is defined in this interval, and you apply homogeneous Dirichlet boundary condition. So under this condition, this is a skew-Hermitian operator. You're going to pick your the eigenfunction with eigenvalue 1 is this function right here, and you can pick L either as a point evaluation or as an integral. This is infinite dimensional, so eventually when we actually implement this, we have to discretize this. In order to maintain the skew-Hermitian structure, I prefer using structure-preserving discretizations. And right here, I'm using what's called the summation by parts method. Now, you can, for the spatial discretization, you can use uniformly spaced grid points. You can also use a non-uniform distribution of the grid points. And here I'm kind of choosing a particular choice here where the spacing is exponentially scaled toward the right. Okay. Now, I'm going to let M be the number of grid points. So the number of ancilla qubits is about log of M. And with these specific choices, then the discretized operator has a very nice form. Of course, first it's skew-Hermitian, but secondly, it's a tridiagonal, and these elements in the interior are actually constant. So it's kind of easier. If you want to kind of encode this, it's probably much easier. You can also think of it as a tight binding model with nearest neighbor hopping. And so when you implement this on the ancilla register, if connectivity is one thing that you are really concerned about, this would be a really good choice. Now, for the vector r here, I'm just going to pick theta to be 2 so that r is a constant. But in this structure preserving discretization, we need to kind of include the integrals. So effectively, this is kind of a rescaled constant vector weighted by the quadrature weights. Okay, so I'm going to make these specific choices, but there are many other choices. Now, after this discretization, how do we think about the error from this finite dimensional approximation? One angle is the following. So ideally, we want this function r to be an eigenvector of f. So I put in this extra parameter here with eigenvalue 1. And what happens is that with this type binding approximation, you can look at the residual error. The residual error is going to be 0 everywhere except the right boundary. Okay, so you can. This is one indication of the error. In particular, if you want to check the moment conditions, you can pick the element L as a location J in one of the computational bases. And then what happens is that the moment conditions will not be satisfied for all orders, but it's going to be exactly satisfied up to order m minus j. So this you can satisfy more moment conditions if you increase m minus j star. Now, another way to think about this is the following. You can take your matrix here and make a rank 1 correction. And if you choose this coefficient just right, then it satisfies all the moment conditions. And because of the theorem that I mentioned before, using this f hat, this new matrix here, you can create a matrix H that generates the exact dynamic. The only caveat is that this matrix here is not skew formation, almost skew formation. So there is only like one extra term at the boundary. That being said, you can use this to set up a reference dynamics. All right, and so if you solve this dynamics with this H hat, you're going to produce the exact solution. And so here I wrote out these different copies of the solutions, right? And you can compare the actual dilated dynamics that you are actually going to simulate or implement. And so they are only off by one term. Therefore, the error between the two satisfies the following error equation with 0 initial condition. And so the way to think about the error term here is that the source is coming from the boundary. And so you can almost think of it as a dynamic Green's function where the source is sitting at the boundary. And that error is going to propagate into the interior. Okay. Now, this extra term that we added here to understand the error can be viewed as an imaginary potential. If this is something that you can actually do on your hardware, then you can actually realize the exact dilation. You don't have to listen to the rest of my talk, right? But I don't know how that can be done. Right? So back to the error equation. One way to understand this propagation of the error from the boundary back into the interior is to look at the continuous case where the operator f is this differential operator. What happens is that this equation is a first order differential equation. It has a finite propagation property. Namely, the error from the boundary will arrive at a point P in the interior at time that scales like log of 1 over P star. Right? In fact, you can visualize it like this. So this three-dimensional figure is showing how the error propagates into the interior. This axis is the time axis. This axis is the t axis, right? For this exact dynamics, if you stay behind this wavefront, you're going to be 0. So namely, the error, the boundary, will not affect you at all. But of course, after the discretization, is no longer true, but almost. Right? Now, suppose that the K here is bounded by K max. And if the K max and T and some of the parameters here, you can think of this as the distance because you're going from M to J star. If this ratio is less than 1, then what you can show is that the error is going to be geometrically, has a geometric decay with M minus J star. Now, what you're seeing in the denominator is a hyperbolic sine function. So at the beginning, we were kind of excited about this because you can increase this parameter here so that this ratio is always below 1, okay? And, but it turns out that although you can do that, but what happens is that when this H is large, the grid is exponentially scaled. Then when you kind of select your solution out from this J star, the success probability is going to be exponentially small. Okay? So, so the way that we satisfy this property, you can think of it as the light cone property or CFL condition, is to make the K and T here to be order 1, and then we tune the rest of the parameters. Okay, so I'm going to pick the T here to be less than 1 over K max, roughly speaking. The theta here is 1, it's 2. And then to satisfy, and then you can make sure that this ratio is less than 1, and then you can pick M to be log of 1 over epsilon. Again, M is the dimension of the ancilla, and log of M is the number of ancilla qubits. And so there's a choice of H and J star such that not only can you make this error less than epsilon, you can also make the success probability to be bigger than some constant, so let's say a quarter. And the norm of this operator is order 1. It's epsilon independent. So that way, later on, when you do Hamiltonian simulations, this part is not going to cost you extra. So that's how we kind of customize the parameters in the dilation. I want to kind of slow down a little bit and mention the kind of comparison with one of the quantum imaginary time evolution methods. So quantum imaginary time evolution aims at driving the system to the ground state by shifting the Hamiltonian so that it's positive definite, and then evolving this in the imaginary time so that the system would eventually converge to the ground state. One way to do that is to use the sigma, the Pauli Y matrix, and build this dilated Hamiltonian, right? So that the original Hamiltonian goes to the off diagonal. You can prepare the ancilla at 0, and then you can evolve this, this dilated operator, and then you can do a weak measurement. The second paper here did it slightly differently. So the ancilla is prepared at the plus state, and eventually you measure at 0. And we can actually look at this method from a dilation viewpoint. Your operator F is essentially this skew symmetric matrix. Your vector R is plus, and your vector L, or evaluation operator, is 1 over square root of 2, 0. Okay? And so what happens is that you can show that this selection, or this choice, only satisfies these 2 moment conditions. The next moment condition is not satisfied. And because of that, your one-step error is going to be proportional to the norm of h squared times tau squared. So in order to maintain the accuracy, this has to be small. On the other hand, our dilation method here can satisfy many, many more moment conditions, and it allows you to choose this h times the step size to be close to 1. Although we haven't implemented this on real hardware, so theoretically, this is sort of better in terms of the accuracy. And so because of that, you can make the step size much bigger. For long-time simulations, due to the light cone property, if k is large, then we have to choose the simulation time to be shorter. And so to get to a long time simulation period, we're going to have to divide it into segments. And after each segment, you're going to do oblivious amplitude amplification. So at the end of the each segment, what you came up with is if you pick your solution outside of the light cone, what you're getting is your solution tensor product with a window with the correct solution, right? And after the oblivious amplitude amplification, you restore the eigenvector on the ancilla and tensor product with a rescaled solution. And overall, the complexity here has to do with how much your solution has changed. So the overall complexity is for autonomous case, A is time independent. For each segment, you can apply optimal Hamiltonian simulations. What you pick up is the norms of these two matrices times the segment length and plus log of 1 over epsilon. But after L segments here, the overall complexity is going to be roughly speaking, the norm of A times T, and then plus this log term. And this part is because these extra pieces are because your solution could be, the norm of the solution could change. For the dissipative problem, the norm keeps decreasing. You get this ratio here. For a system with transient stability, your solution can grow temporarily and then eventually decays. In that case, the solution here, the complexity here is almost the same, but the numerator takes up the maximum of the norm of the solution in the middle. For the non-autonomous case, A is going to be time dependent. For each time segment, you're going to apply Dyson series, right? And then you try to kind of restore the ancilla after each time. And so overall, your complexity looks like this. So the main part is going to be the maximum of the norms of H and K in time times T, and then this log divided by log factors. Now, some of the previous exact dilation algorithms relied on LCU. So one natural question is, can we implement this dilation using LCU instead? Right? And the answer is yes. So starting with this skew-Hermitian operator, you can do a spectral decomposition, right? This is not a large matrix. You can do it classically. And for some special cases, you can do it almost analytically by using discrete Fourier transform. And you can use these eigen functions for both this FH and this identity operator and separate out these eigenfunctions from the exponential. And so then these eigenfunctions will be combined with these two elements, L and R here. What is left behind are these unitary operators, right? And so these are suddenly become a Hermitian operator. And altogether, this is becoming a linear combination of unitary. Now, this doesn't have to be done at the discrete level. You can go back to the continuous level and apply Mellin transformation and derive a formula like this. Now, can we apply this to some application? Right? Now, I came from applied math, so the first thing that we think about is wave equations. And so the application that we actually considered is viscoelastic waves. So this is a two-dimensional PDE, right? And this is the divergence, and this is the gradient. So this part is sort of the second-order wave equation. But there could be viscosities or dissipations and things like that. And you can apply direct finite difference approximations to discretize these. This is the actual dynamics. So what you're seeing is sort of the pressure field. What you see here is that originally we set up two wave sources that shape like Gaussian. They start to spread, and with periodic boundary conditions, they start to bump off of each other and creating these wave fronts. And we did simulations on classical computers, and we simulated the corresponding Schrodinger equation from the dilation of this PDE. So I'm just going to show you one of the figures, so we can reproduce the exact results here. What I want you to show you is this light cone property. So what I plotted here is the pressure at some point, but the history of it, right? So this is the history of the pressure at some point. The exact solution is the solid line, right? And then the rest of the curves are the solutions that you post-selected after simulating the dilation. And so these are the solutions that you get after post-selecting at different locations. What happens is that if you pick this post-select location to be 1/2, then you're kind of too close to the boundary. And so somehow around this time, the boundary error is creeping in and starts to generate some error. Now, if you move this selection point to the left, so this is point 1, then your solution is going to stay really good until I think somewhere here. And if you post-select further to the left, then you don't see the difference. So at least in this time window, the two solutions are exactly overlapping. Okay. So it's just supposed to kind of confirm the light cone error. Now, after we finished this paper, we started to think about extensions of this. And so one natural extension is linear SD system. And so what we considered is a system of linear SDs. This is written in the ethos form, and the noise is multiplicative, but if you have additive noise, you can introduce auxiliary variables and convert it into multiplicative noise. Now, you can also try to understand the stability of the linear SDE system. A standard way to look at the stability is to look at the mean square. And this is how we test the stability of some SDE solvers, just like stability test for ODE solvers. And so what happens is that the average norm squares is going to satisfy this identity. And this matrix K here, if it's negative definite, then the right-hand side is going to be negative, so the norm is not going to blow up. Okay. More generally, if this K is less than some number of the identity, then you can derive kind of integral inequality and derive a bound on the solution, the mean square here. On the other hand, in open quantum systems, the stochastic dynamics that we usually look at is the stochastic Schrodinger equation, right? And so over there, the VJs are the jump operators, and there is this dissipation here in the drift term. And the stochastic Schrodinger equation can unravel the Lindblad equation. It can also motivate some of the Lindblad solvers. but it has this really rigid structure. You can think of it as the fluctuation dissipation theorem. This V here will show up here as 1/2, roughly speaking, V squared, right? On the other hand, the general SDE may not have that structure. In fact, the general SDE can only be written as the stochastic Schrodinger equation if this matrix is identically 0. And so there's this mismatch. Now, can we apply a dilation and turn these SDEs into a quantum dynamics that we are familiar with and that can be simulated on quantum circuits? Okay. And this is what the question that we try to answer in this more recent paper. One route is to apply some simple algorithm to discretize the SDE in time, for example, the Euler-Maruyama, and turn it into many, many ODEs, right? Because for each choice of the Wiener process, you get a system of ODEs. And for these ODEs, you can use the previous dilation schemes. And so this paper used the Schrodingerization algorithm. So this is one way. You can turn it into many copies of Schrodinger equation. And we tried a different route. What we want to do is we want to establish a dilation that map the SDEs to stochastic Schrodinger equations, right? Whether this is a better approach than the previous one, I don't know, but it's kind of just a fun exercise to do. And toward this goal, what you can do is you can first write down this matrix here. So A is the drift, and Bj is the diffusion coefficient. And then you add them up. And you apply the same decomposition to this matrix L. So this part has the familiar formation part, and this part is, we call it K again. This K is the same K that you saw in the previous slide, right? And so if K is equal to 0, then this is already a stochastic Schrodinger equation. You don't have to do anything. When K is not equal to 0, we are going to make it formation. So by, again, outside of this I here, by using the same dilation formula. Okay? And you can use Schrodingerization thing. I think maybe linear combination of Hamiltonian simulations as well. For the operator B, I'm going to use the trivial dilation, and I'm going to think of the new operator as the jump operator. Okay? And the end result is this stochastic Schrodinger equation with solution per psi. So this H tilde came from this dilation step. This Vj came from this trivial dilation. And pathwise, you can recover the solution of the SDE by, again, applying this evaluation operator on the solution of the stochastic Schrodinger equation, right? And so this way, we can simulate, in order to simulate the solution of the SDE, we can simulate many, many quantum trajectories, right? And then apply weak measurement, for example, to get the solution of the SDE. Now, it turns out that this similar light cone properties still hold, right? And so you assume that this ratio here is less than 1. And then what happens is that if you look at the square error of this chi, so this chi previously is the error between the exact dilation and the approximate dilation. And here, this chi is going to be a pathwise error. Right? The mean square error, it has this geometric decay. Okay, so you can take the same m here so that the right-hand side is less than epsilon. This is a direct view of that. So this is kind of a numerical experiment on a 3x3 SDE system. And this is kind of an indication of the icon property. So what happens is that if you post-select at the point 4, the error is starting to show up around this time 0.4. But if you post-select at point 1, then at least in this time window, you see very little error. Now, one of the scenarios that this can be applied to is you solve the SDEs and you're estimating some quadratic statistics. For example, the covariance matrix. It turns out that you can estimate these quadratic statistics by simulating the Lindblad equation. Right? So suppose that the quadratic random variable that you try to estimate is written in this form. You can write it as the trace with the covariance matrix. For the Lindblad equation, this is the second moment of the stochastic Schrodinger equation. And what happens is that this second moment and the second moment of the original SDE correspond to each other according to this formula. Now, if you go back to the quadratic random variable, you can write it as an expectation now, with this being the new observable. This L is not normalized, so this pi is definitely not a projector. Okay, but you can apply block encoding and then estimate amplitude amplification to estimate it. So that's one direction you can pursue. The other direction is to generate trajectories. So let's say that for some applications, right, we want to prepare trajectories. Okay, so what we can do is we can prepare quantum trajectories, and after that, we take out the solution of the SD. To generate the quantum trajectories, the simplest idea is the Euler-Maruyama method. Right? So this is like written like this. This delta W is the Brownian increment. It's a Gaussian random variable, mean 0, and the variance is tau. To realize this on the ancilla, you can approximate this delta W using this binary random variable. And so the way that you do it is by putting H in the diagonal, and the off diagonals are these jump operators, and build this unitary. And then to kind of apply these random terms, you do something to the ancilla. Right? So you apply this unitary so that maps 0 to plus. If Qc is positive, Qc is either positive or negative. If Qc is negative, you apply that to negative. So that creates this random term here. But altogether, this is consistent with the Euler-Maruyama method. That's only a first order method. So you can also push it to the second order, and this has a nice connection with some simulation algorithms for Lindblad dynamics. You can base this off of the Ito-Taylor expansion for the stochastic Schrodinger equation. So I combined a lot of terms so that we can kind of see these different random variables, the deterministic terms, and these are coming from stochastic integrals. Now, to implement these on the ancilla, you can introduce a discrete random variable that matches with Gaussian up to order 4. Okay. And then you build this dilated Hamiltonian here, and this alpha is trying to kind of connect these 3 random variables. And this W here, right, and applying to the ancilla kind of creates these or realizes these random variables. And the matrix here is very similar to what we wrote in our previous paper with Len. In general, these methods are second order in the sense that the statistics or expectations have an error that scales like the step size squared. Okay. I think I'm getting close to the end of my talk. So today I talked about some dilation schemes that map linear non-Hermitian dynamics to Schrodinger equations so that we can do Hamiltonian simulations. I also talked about mapping linear SD systems to stochastic Schrodinger equations so that we can apply either Lindblad simulation algorithms or quantum trajectories. In terms of the applications, one application is PDEs. We also have a student now working on implementing this in quantum imaginary time evolution. Now, one of the trivial applications is to non-Markovian open quantum systems, especially when people try to develop these non-Markovian dynamics by using Markovian embedding. So you're writing down quantum trajectories, but they are embedded in a much bigger Markovian stochastic differential equations. These stochastic equations do not necessarily give you a bigger Lindblad equation. However, using this stochastic dilation scheme, you can immediately map it to something that looks like Lindblad in a bigger space. Now, some of the open issues is that one is the light cone conditions. I don't know how much we can push further, whether there are some clever discretization schemes to improve the light cone property so that you can simulate the dynamics longer without doing a lot of segments. Another is like, to look at other non-Hermitian physical systems, like for skin effects. I don't know whether this will have a simple implementation towards that. Now, for scientific computing problems like PDE or ODEs, nonlinear problems are difficult, and you can think of Carleman as a dilation. You can actually write down the Carleman linearization in the same structure as I wrote down at the beginning. The only difference is that the starting vector R is a nonlinear mapping. And there are other choices, but the problem is that in general, these dilation schemes have a finite convergence radius. Now, the stuff that I talked about are coming directly from these recent papers. And if there are questions that I cannot answer today, feel free to email me and I'm happy to discuss, and I'm happy to listen to your comments and suggestions. So with that, thank you for your time.